Okay, so recording has started. Hi Nigel. So you are the only one right now. I guess probably because the this week's assignment is easy, so people are not joining today. Anyway, the lecture is recorded, so they can watch it later. Have you joined before, or this is your first time attending the live session?
Actually, I was joining the other batch.
Okay, so you have been part of the live section of that
Yeah,
other TA Rajdeep. Okay.
yeah, but the last two lectures I missed. So
Okay, no problem. Anyway, these lectures are available on YouTube, so you can watch anytime. Okay, that's not the
okay.
issue. Uh, what is this? Yeah. Okay, so just I will briefly introduce about me, and then we can proceed ahead. Okay, so let me go. So this is the basic course on Aspen simulation software, right? It's a beginner course and taught by Professor Prabirkumar Saha. So I am Bhavesh Moorjani, and there is another TA Rajdeep whom you already know. So we both do this live interaction sessions where we interact with students, we solve different problems so that you get more familiar with the simulation software and the use of it as a chemical engineer. Okay, so my live interaction session happens every Tuesday from 6 to 8 p.m., while I think Rajdeep is taking on Saturday's session. Okay. uh, so brief about me, I have done my bachelor's from MS University Vadodara. I have done my chemical engineering from there, and currently I'm doing PhD at IIT Bombay. So I was exposed to Aspen Plus simulation software in my UG curriculum, and currently I'm teaching you guys, like in a way helping you guys to learn or understand it more. So these are the contact details. If you have any doubts, you can try to contact me here via LinkedIn or via email. I will try to respond you within 2-3 days. Okay. So the way this session will go is so currently sir has the week 3 4, sorry, not 4 5 6, that if you will see all the lectures, they are associated with the property analysis for pure component, binary component, regression of various model parameters to achieve better accuracy, or some or the recent this week 6 lectures which are related to the optimization and sensitivity analysis. So last week we had done some pure and binary component analysis, and this week we will again continue with that. So we will first do some binary component analysis, and then we will move forward with the regression part as well as the optimization and sensitivity analysis part. Okay. So Nikhil, do you have access to Aspen Plus with you right now?
Yes, I do. I have access.
So will you be able to share it? So the way I generally do it, like last time we had did was that I will solve one problem, and then some student from the online session can do other problems. So if you are okay with it, then and you can share your screen, and then you can solve it also. That way it will be more interactive and
No, sure. So just I need to open the Aspen now. Just a minute.
yeah, it's okay. I mean, first I will start, and because
Yeah.
that another reason is that sometimes Aspen Plus takes considerable amount of time to load in my PC. So in that case, it's helpful if some other students has already preloaded in them. Okay. Anyways, so
Sure.
we will start with it, and then we can see how it proceeds. Okay. So
Yeah.
first
I'll keep
exam,
it ready.
yeah, sure. Thank you. So first example is that we have to compare the ideality of phenol aniline mixture through analysis of TXY and XY diagram using ideal, NRTL and Unifac model. Okay. So create a new Aspen Plus simulation file. So we have two components, phenol and aniline.
Excuse me, sir. I couldn't see your screen.
Oh, sorry, I haven't started sharing. Oh, sorry, pardon me. Now you can see it, right? Yes.
Yes, yes.
Yeah. Okay. So I was just briefly introducing myself. Anyway, that thing is recorded in the lecture. So this is just a brief introduction about me. Okay. If you have any doubt, you can try to contact me via LinkedIn, or you can write it mail to me. Okay. And one more thing I would like to mention to you and other audience also, we will watch it later, that if you guys have any doubt related to, specifically related to assignments and assignments answer, so the recent assignment number 5, there was issue with the question number 9, where the answer was asked in probably Newton per meter square, and the actual answer, the correct answer was given in kilonewton per meter square. So if you have such sort of a doubt, I would ask all of you to directly, if you are sure that there is some mistake or discrepancy, then directly write to Professor Saha, because I'm not designing those assignments, like I'm not creating those assignments, so I really don't know. So it's like two-way communication, that some of you try to contact me and then I contact sir. So rather than, you can directly contact to sir also, he will respond to you. Okay. So for question number 9 in assignment 5, sir has updated the answer key, so people will get mark accordingly. And same goes for the, I think, question number 10 for assignment 4, where that U shape Gibbs free energy plot was there. Okay. So just saying that if you are sure there is some mistake in the assignment evaluation, you can directly write to the sir. He will solve your query, because this way it becomes a two-way communication, rather than that you can directly contact to sir. Okay. So as I was saying, that first we will do some binary analysis, and then I have set some problems for optimization and sensitivity analysis part. Okay. So first problem is that we want to compare the ideality of phenol and aniline mixture. So add phenol first. What happened? Yeah. Phenol and then aniline. Okay, so we have added the component. Now the methods that have been asked are three methods: ideal method, NRTL, and then unifact method. So first, let's add the ideal method, then NRTL is also there, NRTL and unifact. Is it changing? Okay, so all the methods are added. Press next and do the property analysis. So we have to compare, the question asks that compare the ideality of phenol aniline mixture through TXY and XY diagram. We have to use this three model. So what we will do is, like, when we have ideal method, we will generate TXY plot with the ideal method, then NRTL and unifact, and also we will download some NIST data for this phenol aniline mixture through NIST system, and then compare the actual experimental data also. That's it, processing. should not take too much time. Let me result available with warning. What's the warning? Warning in physical property system. The following conventional component were not in a data bank. Phenol and aniline. Why? Components are correct. Maybe it's a method warning. So let's see. First, what we will do, we will go into the binary analysis. We want to generate a TXY plot. So TXY is selected. In the calculation option, first let's select the ideal method. So I'm evaluating the data at currently at 1 atmosphere only. Okay. Run the data. This is the issue. Meanwhile, can I open this? No. Okay. So plot is available. Let's see how it looks. So this is how TXY plot of phenol and aniline looks. As you can see, the two-phase regime is very narrow for a given 1 atmospheric condition. Both the dew point line as well as the bubble point line, they are very fairly close to each other. So this is with the help of the ideal method. Now let's see how we stand when from the experimental point of view. So what we will do, we will retrieve the binary data for phenol and aniline from NIST. Do retrieve the data. Just a moment. Okay. Yeah. So here you can see we have one binary VLE data, and that is, but it's at different temperature. So we have one data, but the temperature and pressure conditions are different, so we cannot directly use this data. but we have two data points which are at 1 atmosphere. So let's see if I save this data. And can be modified. So what I will do, I will just keep the data of 1 atmosphere to compare with our method data. Okay, and if we see TXY here, okay, there is one point here and another point here. So there are 2 points only. Maybe let's forget about it, since the data point are very few. It won't be a good idea to compare it. So rather than, we will just compare the ideal method with the UNIFAC and NRTL method. Okay. So this is the TXY plot from the ideal method. Now again go to the analysis, binary analysis. We want to generate another TXY plot from, so this time let's select the NRTL method. So earlier the option was ideal, now binary 2 is with the NRTL method, same TXY plot. You can generate third one also, binary 3. So binary 3 is also TXY plot, and the calculation option that we will select is UNIFAC. Okay. So run the analysis. What happened? It's running. Okay, we have another student. It's taking longer than usual. So this one binary 3, it was through UNIFAC method. We can rename this also. So let me rename this as UNIFAC. Okay. This plot is with the ideal condition. So write it as ideal. And second binary 2, which was with NRTL. Let me run this also. So this is the binary 2 plot. Okay, and this one is NRTL method. We can club all these plots into the one plot. Let's say binary 1 and binary 3. Make one single y-axis. So as you can see, this way this label has changed again. But if you with the unifac method, we get this kind of a azeotropic curve, while with the ideal and NRTL method, we get this sort of a curve. Now the phenol and aniline mixture, it's actually a non-ideal mixture, so it will deviate from this ideal behavior, and I think the unifac method will give the more correct answer. But the data set that we have available from the experiment is that not the desired pressure condition, like we have very limited data, so we cannot directly compare it. But you can see if we are changing the methods from the ideal or NRTL to going to the unifac method, we see a significant deviation in the VLE plot itself. So for that, we need to compare exactly which method to use. We need more thorough experimental data set which we can compare with the data generated from our model itself. So this was the first question, which had compared the behavior of phenol aniline mixture, which is in a way actually a non-ideal mixture. So with the ideal, NRTL and unifac method. Then the second question is again kind of a similar background, that where you have to compare the ideality of ethanol acetone mixture through TXY and XY diagram. So what I will do, you guys can try out this example also. So again, you have to add the ethanol acetone as a component, select this 3 method, generate a plot, and try to see if the NIST data set has the experimental data available for ethanol acetone mixture. If yes, then we can compare that data with the model data generated from all 3 methods and can decide which method will be more suited for our user case, like for the ethanol acetone mixture. Now question number 3 is that we have given water isobutanol binary mixture at 1 atmospheric pressure, and we have been asked like which property method among NRTL, Peng-Robinson and unifac is better suited. We have been asked to improve the parameters through regression and check whether the change in pressure helps in the separation of water isobutanol azeotrope or not. So here what we will do, we will again plot water isobutanol data, but this time instead of just comparing the experimental data with the model data generated, we will try to modify model parameters such that it fits the experimental data. To do that, do any of you want to share your screen and run Aspen Plus there? So that way it will be slightly easier for me, since it takes time to run the analysis in my PC. Nigil or Tanmay?
Let me try from my side.
Yeah.
So.
Okay. I will stop presenting. You can share your screen. So basically, because of this recording and running Aspen Plus together, my PC cannot handle it. You can share your screen now. Yeah. So yeah, we can see.
I hope you can see the screen, right?
Yeah, we can see your screen. So the 2 components that are given is water and isobutanol. So add water, isobutanol. Okay, and the methods are sorry. no match. There is no match. Isobutanol, that's correct. Right. It should come without also. Okay.
We'll have to click equals.
No, I mean if it contains, then also it should show isobutanol. Equal will show exact match. Okay, yeah, isobutanol is that. Add that. Go to the method, press next. Now the method one is Peng Robinson. So select Peng Robinson. Yeah. Then NRTL and Unifac. And last is Unifac. Okay. So now you can press next. Next. Run the analysis. Okay. So first what we will do, we will see what NIST data are available. So can you go to NIST? Binary mixture. Okay. Now we need a VLE data. So you have binary, yeah, binary VLE data, isobaric data. Can you open 001? So this is at total pressure around 1 atmosphere. So maybe we can select this data. Can you see other data also, 03 or something? 101. And okay, so maybe 003 we can select. Okay. Can you save this data? Yeah, hide that part. Okay. It's auto selected, you can just press OK. Yeah, so we have this data. Now you can see the TXY plot from the top right. No, cancel it out. Yeah, so on the top right part, on the top toolbar, you can see the TXY plot symbol. Click on that. So this is the experimental data. So we have only X. Oh, it doesn't contain the Y part. Can you go to that data again? Yeah, click on that and go to the data part. Oh, sorry, it only has the X component data. No, we will need both X and Y. So can you go to the again NIST data list? Yeah, the first one, VLE001. Check it out. Oh, it has both the vapor fraction as well as liquid fraction. So maybe this data will be helpful. So you can download this one. Okay. Yeah. See the TXY plot from here. So this is how it actually looks. So as you can see, it's a non-ideal mixture. and it forms the azeotrope. Okay, so now we will compare this experimental data with the all three methods. So first let's try with the Peng-Robinson equation of state. So go to binary. Go to calculation option. Calculation option is there, just right there. And instead select the Peng-Robinson part. Okay, go to binary analysis again, and we have to select the not run. We have to put the exact pressure value for a better accuracy. Okay, so Newton per square meter. Yeah, first one. Select the first unit instead of atmosphere. Go up, Newton per meter square. Yeah, and what you do, just copy paste the pressure value from the your BVL 001 data. From the data point. Here you have pressure value, right? So it's 101,000. You can just paste this value there. Okay, now run the analysis. Okay, so this is the Peng-Robinson data. Obviously we can see there is a huge discrepancy. Label it out. And you can now merge this plot with the experimental plot. Yes. So we can see that is too much. Okay, just combine the y-axis first. Sorry. Right click on the graph, y-axis map. Yeah. Single y-axis and club it. Okay, so the experimental data is at much higher temperature condition compared to the water. Why? This should not happen actually. Okay, so there is much difference here. So what we will do, we will first try to fit this data. Both are at same 101. Yeah, pressure value is same. Okay, so there is a difference. Okay, so what we will try to do, we will try to do fitting of Peng-Robinson data so such that it matches with the experimental trend. So for that we have to go in the regression part. So can you go to the home? Yeah, in the regression on the top toolbar. Yeah, select it, click new, DR1. Yeah. So first we want to modify the Peng-Robinson method, so select that. Okay, yeah, Peng-Robinson, and the data set will be data set. You can click the option, and we want 001 data set, right? So first data set, yeah, select that. Go to the parameters option. Select it. Now here we have to provide how many parameters we want to modify for this regression. So first select the type. So this is a binary parameter that we want to fit. Then name. If you will see various options available. So right now the PRKBV, can you just put your cursor there? It's written that Kij binary parameter for Peng-Robinson equation of states. So we want to modify this first. Can you go put your cursor below that PR? Sorry. This is also a Peng-Robinson binary parameter. So first what we will try to do, we will modify this PRKBV. So select that. And then element. So you can provide the element number as 1. So this is our first element. Component. Select water or water. And the group will be isobutanol. So this is a IJ interaction between water and isobutanol. Now on the second column, you can copy paste this column also. Select the complete column. And you see the copy paste option right there. Okay. So the parameter will remain same. So it's see here it's parameter is Lij, that's the way it's written. So if we are setting the Aij is not equal to Aji, in that case we have to provide both from water to isobutanol as well as isobutanol to water. So select PRKBV again on the second column. Yes. Element number will go to 2. And select isobutanol first and then water. Okay. So first let's try to see whether changing only 2 parameter helps us or not. Do the regression, run it from the top itself. You can just run it. Yeah. Okay. So regression is done. Now we can again plot the binary data from Peng-Robinson equation and see whether the discrepancy has gone or not. So go to binary. So see there is some difference that has occurred. Now we can try to merge it with the experimental data. No, this won't change. I think you have to re-perform it. Can you merge it again? No, it has, see, from previous step it has changed and the curve has shifted to a higher temperature condition compared to the previously what it was. Okay, so it has done some improvement, but for further refinement we can, so right now we had only selected 2 parameters, but in the regression part itself, if we provide another parameter regression, like more parameter regression, then we will get a better improvement. So you can go to regression part again, you can close this plot. Yeah, go to the parameters. Now we will select that another copy paste this column. Instead of this, select PRKB, PRLij, yeah, and then water and isobutanol, component 3, water isobutanol. Yeah, same parameter for isobutanol water. So copy paste it. Number 4, isobutanol and water. Okay. Now run the regression. Data regression completed, results are present. Yes, okay. What is the warning? Let's see. Can you click on that DR1? Constraint not satisfied for this case. I'm not sure. First let's see how the plot looks. Go to the binary analysis plot. You can do update parameters probably and see. Component ij, update the parameter, do okay. Yeah. Run the binary analysis now. So see, there is again improvement over the left hand side of the curve, but right hand side parameter is still not matching. So this could be some limitation of Peng-Robinson equation of set itself to match with the system property of your water and isobutanol. Then in that case we can look for the other method, NRTL or UNIFAC, whether that method matches with the data of experimental or not. Since in our question what has been asked, like which property method among NRTL, Peng-Robinson or UNIFAC is better suited. So what we will do, we have seen that with Peng Robinson we try to improve these two parameters also, but it's not exactly matching with the experimental trend. So rather we will first now see whether the UNIFAC method or NRTL method is giving better result or not. So instead perform a new binary analysis with the UNIFAC method. You can close all this plot if it's okay. Yeah, close this. Hey, close everything, it's fine. Go to I think required input is incomplete. Probably you have to rerun it. It has added PRKBV parameter. So can you do next? Press next option. Okay, so one more parameter is added. BPVL not complete. Parameter name PRKBV CID water missing. Value of at least one element must be specified. Okay, so it has added extra component here. Right click on remove the second row here if you can. Delete the row, yeah, and run it. So in the regression it has added an extra parameter. Regression we don't want to do, close it. Now just see binary, go to binary plot on the top part. We will do a new binary analysis of TXR with the UNIFAC method. Okay, see the calculation option first. So UNIFAC is selected. Enter the pressure value as that Newton per meter square 101,000. Okay, and run the analysis. It's okay. Let it take its time. And I have this under the data also. No plot or table produced due to calculation error. Press do OK. What is the error here again? Error while processing. Can you do reset simulation first? So on the top toolbar you see the reset option adjacent to the run. So reset it, purge all the parameters, do OK. Yeah, press OK. Then now on the your left panel, remove that regression part. So go down, yeah, DR1, right click on the DR1 and delete it. Okay, yeah. Okay, now just do next and run the analysis one more time. PPLB is also not complete. Okay, so what has happened because of the regression, it has added the extra parameters which value we don't have. So maybe just scrap the simulation and run a new one. So don't do it right now. So what you can do is like scrap the simulation when you are facing such issue, because what is happening, like the regression that we are trying to do, it has added the extra parameter which has not converged, and now it's asking us for its value. So rather than that, you start a fresh simulation with the unifact method, put on the compare the unifact method with the experimental data. If that matches with the trend, so I assume for this example unifact method gives a better trend for to match with the experimental data, and there to get a better accuracy we can again do the regression. So right now we did the regression for the Peng-Robinson parameters, okay, 4 parameters of Peng-Robinson. There again for the unifact method we can do regression on the multiple parameters of unifact method and then get the same trend, okay. So that's how we can decide like which method, so the question had asked us like which method is better suited out of this 3, NRTL, Peng-Robinson and unifact, and how to improve the parameter through the regression, okay. So yeah, maybe you can close it, it's fine. You can unshare your screen, I will take it from here. Okay, thank you, Nikhil. Another question it has asked is, so let me do one new simulation. Yeah, let it load. Okay. Another thing it has asked check whether the change in the pressure helps in the separation of water and isobutanol isotope or not. So what has happened, like the experimental curve you have seen, there was one point where isotope was forming. So if pressure change, so that azeotrope was forming at the 1 atmospheric pressure, but we have to check if we change the pressure, if we increase the pressure, whether the separation will be possible, whether the azeotropic condition will change or not, okay. So for that you can, on the same TXY binary analysis itself, you can provide multiple pressure conditions, 1 atmosphere, 20 atmosphere, 50 atmosphere, and on the same plot it will give you a different TXY curve. So then you can compare whether at what pressure condition you for the given composition you can do phase separation, like you can separate out the vapor and liquid, okay. Question 4 asks for the same part, that you have to repeat the above problem with this benzene and cyclohexane system, okay. So there are multiple same examples. What I will do, I will go with this is also a regression part. Instead, experimental VLE data is available for benzene ethanol system. So here instead of taking data from NIST, we have data available from the experiment that we have to provide, like we have to put in manually, and then we have to do regression. That can also be done. So procedure will be same, just the data part that we were downloading from the NIST, instead we have to write it manually from the experimental data that has been provided, and then we have to see whether the Wilson method matches with that data. If not, then through regression we have to optimize the parameter, okay. So this all question number 4, 5, 6 are on the same background. Then we have question number 7, which says calculate the K value diagram for ethane ethylene binary system using ideal and unifact method. So let it run and I will move forward. So many of the data are same. Question number 9 deals with the regression for pure component analysis, where the toluene vapor pressure data is given with the temperature, and we have to regress the vapor pressure data using the NRTL method and compare the experimental and NRTL model, okay. So we will do quick question number 7 and 9, and then we will move forward with the question number 10, which is also small, like finding the azeotropic condition, which is similar to the what current assignment you have, where you have to find the azeotropic condition for a given mixture, okay. And then after we have 2 good example on the data regression part. So I think that will be sufficient to cover this week's aspect. Okay. So we have been given that ethane and ethylene binary mixture, and we have to compare their K value. What is the K value? You guys know it? It's a ratio
It's a
of
reaction constant. Okay, XY ratio.
yeah, it's a ratio of y by x for a given
Yeah.
component. Okay. Yeah, so currently we are talking in terms of this equilibrium data, and so that's why in that sense. Okay. So we have ethane. Ethane, ethylene. What I will do, I will add toluene also for that question number 9. Oh, it's a wrong spelling. Sorry. UL.
Sir.
Yeah.
Yeah. The what is the reason we are doing regression? It is to fit the plot into
So
like.
basically the various methods that are available, whether it's equation of state method or activity coefficient based method. Okay. So each works on some sort of assumption, and for so there are various parameters available for each method. Let's say if I talk about Peng-Robinson equation of state. Okay. So if you will see the expression of that equation of state, like all the equations that it uses some uh, parameters which are either calculated based on the critical temperature pressure data of a given component. Okay. Now based on that it will give you some trend, but it's possible since it's a generalized method, so it's not that one method is suited for all of your component. Okay. So mm, whether let's say you have selected one method, right now we were looking at Peng Robinson, and then we want to work our simulation based on the that method. But if it's deviating for your actual condition, so we saw that experimental data has a different value, and the Pang Robinson of equation of state, the dxy plot calculated from that also has a different value. So there is this discrepancy. So this regression is done to modify uh, the parametric value such that the model data are exactly matching with the experiment, so for a better accuracy. Now with this new modified model parameter, we will use this in our simulation part. So right now we are just doing the analysis, we are not going into simulation. So let's say I want to design the flash equipment or a distillation equipment based on this method, but I know, like from the experimental data available, that I know that see experiment trends are different compared to what I'm getting from any model. So in that case my design will be also different, right? If I just do take the parameters available from the Pang Robinson without checking or doing regression, the actual equipment design will deviate from the real condition. Okay, so it's not useful. So in order to achieve that design which matches with our experimental requirements, what we do, we tune the parameters so that whatever calculation we get from our simulations are better or accurate. Okay, so that's the sole purpose. Did you got my point what I'm saying?
Yeah, yes, sir.
Yeah.
But we know that actually in some cases, like unifact method is more suitable. Even though then we are
Hmm.
doing a regression based on Peng Robinson.
Yeah.
Uh,
Uh,
Unifact is the best suited method, but even though then we regress, do the
no,
regression for Peng Robinson method.
no, that was just an example. It's not, and again, it's not that Unifac is best suited for every condition.
No,
So,
not every condition.
huh,
For any particular condition, if Unifact is the best suited method,
hmm,
uh,
huh, then you can
and you,
move forward with the Unifac method if you find that the Unifac parametric data gives you a better result, which are matching with your experimental trends. Then you can go ahead with that. Or you
okay,
can further modify it again. You can also do the regression parameter. So at the end it comes down at what kind of accuracy level you want to achieve in your simulation. Okay, so
okay,
right now from this assignment point of view and other stuff, it's just to get used to and to understand how various thing works. Okay,
okay,
but it has an implication that when you are doing a real simulation, like which has some practical implication, then you have to consider this aspects also. Okay.
okay, thank you.
It had the wrong spelling, sorry. Come on. Okay, so first we have, sorry, ideal method, and then unifact method, another one is NRTL. So I'm combining both the questions together, that's why I'm selecting. So first question 7 has asked to find the k value from ideal and the unifact method, and the question number 9 has asked the NRTL method. Okay, for the toluene. So all the methods have been added. I can go to the binary part. First, question number 7 says the calculate the k value diagram from ethane and ethylene binary system using ideal and unifact method. Pressure conditions are not specified, so right now we will select the atmospheric condition only. Okay, yeah. Do you have any question? Okay. So first, ideal method and run the analysis. Maybe Nigel, if you can share again your screen and we can use your Aspen Plus, if it's okay. Yeah.
Let me share.
Thank you. Yeah. So. Yeah, it's loading. Is it?
This will take a little bit of time.
Yeah. Okay.
Once it is loaded, it is okay. It will run.
Yeah. I got it. Mm-hmm. Maybe you can restart it if it's possible.
It's taking. It is taking much long time.
Yeah. The same thing happens with me. Now, along with the recording, this stuff becomes very slow. Okay, let me try again in my. If it turns on, then we can work, or we will work with your piece.
It's now ready. Okay.
It's ready. Oh, so can you share it? Your screen is not shared. Now we can see it. Okay. So add ethane. Ethylene. Yeah. Okay. Let's avoid toluene. I mean, you have to add the data for toluene, so let it be. Press next. Select the ideal method and unified method. Okay, now you can directly go to the binary part. You don't have to run it. Go to binary. First select the ideal method. Yeah, this is around 1 atmosphere. So run the analysis. So here what you will see, we have been asked to plot a K plot, right? But in the analysis type where TXY is selected, can you go and see the other option? Click on TXY, drop down menu. It's not showing. It should show the
K
other.
value, right? We are plotting the K type, right? K. It's not showing.
Okay, anyway, so there are other options of PXY and probably YX, but there is not K plot directly available. So for that we have to run a TXY or PXY. So right now we will run TXY, run the analysis. Right now here itself, if you will go to the resources instead of TXY, can you click, are there other options showing of KXY? Go to the result of binary one. You can click on the result tab. Yeah, here only on your window, on the top part. How would I see? Click on the binary one input on from the left hand side panel. Okay. Okay.
Here
now you see the result
from the top.
Yeah, from the top, yes. So you have TXY, TX option, you will have K. So this is the K plot for ethane and ethylene. So you can see the K value for ethylene is much higher since it's it's unsaturated, so which has a higher, what should I say, the boiling point. So it's like more volatile compared to the saturated ethane. Okay, so that's why its K value is higher. So this is with the ideal method. Now we can same compare the unifact method also. So go to home, do another binary analysis. Yeah, binary 2, check the method is unifact. Okay, and run the analysis. Okay, now go to binary to input. Yeah, okay, so it's a K. You can see, can you try and merge the both the plots, see whether this difference is coming or not. Just label any one of them. First change the label so that we will be able to differentiate. That's okay, I mean, if you have done. So that is some difference. I mean, particularly for ethylene, the difference is more compared to the ethane, where lower. Okay, you can change the y-axis, make it a single y-axis. Okay, so you can see at lower fraction for both ethane and ethylene the difference is less, but at the higher fraction of ethylene you can see there is a much discrepancy between the ideal method as well as the unifact method. Now to select which method to go for, then again one can look for the experimental data or the literature data that is available, and based on that one can decide whether which method to select. Okay, so this is a basic example. Another one quick example that we can do is question number 9. You guys can try it out. So that is again regression, but for a pure component, where toluene vapor pressure data is given for different temperature, and then you have to regrade the pure component parameter for NRTL method. Now what you will find there is that both the NRTL method and experimental data are almost matching. So in a way, regression is not needed. Only there is 1 point difference. So if one wants to work on that and minimize that error also, one can do that. Okay. Now Nikhil, can you do another new simulation, start a new simulation? There is one example of finding the azeotrope which is similar to your assignment. Now will it take time? Have you started a new simulation? It's loading, is it?
Still loading.
Okay. Meanwhile, let me check it in my PC also. So we have acetone, methanol, and chloroform.
Yes, sir, it's loaded.
It's loaded. Okay. For us, it's still stuck at your previous screen. At least for me. Can you reshare your screen? Mine is also working. So we have acetone, methanol.
Now is it visible?
Yeah. Okay. So then add methanol. And last component is chloroform. I think chloroform you have to search. Even meth. No, it's working in mine also. Is it loading?
Chloroform is not loaded. Ah, yeah.
Okay.
Chloroform. Okay.
Have you added it? I have also added it. So, okay. Go next. And use the NRTL method. Okay. Press next and run it. You can run the analysis.
Run it.
Yeah. So there is one thing, while you are doing this next, you get this option of estimate parameters using Unifact. So sometimes there are this missing binary interaction parameter for a given selected method. So in that case, one can use Unifact method to estimate that parameter to improve the accuracy. So not all the time this parameter will be updated if you select the estimate using Unifact method. You can just tick on that and run it again. We will see whether parameters are updated or not. Run it. So So you can see parameters are same, so it has not changed anything. Okay, anyway, now we want to see the azeotropic mixture that is formed for this three component. So go to the ternary diagram on the top right part. Yeah,
We click azeotropic.
actually you have shared your only one screen, so I cannot see the pop-up window.
Okay, just a minute.
Share your entire screen, then it will be useful.
Okay. Yeah, sir, it is visible now.
Yeah, it's visible. So what we will do in generally we do this continue to Aspen plus ternary diagram, but right now we will use distillation synthesis use distillation synthesis ternary map. Okay, so that has been explicitly asked in our question also. So when we do that, now here with this method also we can see whether how many azeotropes are formed. It gives us actually the data in a report form that we can report. So here pressure value selected is around 1 atmosphere. So if you will click on the pure component, the output part, we can see the boiling points of all three component, right? So these are the boiling point for all pure component. If you will go into the azeotrope part, so this gives us the binary and ternary azeotrope formed for the this methanol, acetone and the chloroform. So you can see number of component. So there are mentioned 2, 3, 2, 2. So number of component 2 shows a binary azeotrope and 3 will show the ternary azeotrope. Okay. Then go to the singular point part. So singular point will show these specific what should I say? The important points in your ternary diagram. So this 1, 1, 1 shows the boundary of your ternary diagram. Okay, and then you have azeotrope as well, both binary and tertiary. You can see the report also. So report kind of gives you the this data form like sheet form. So rather than using the ternary diagram itself, we can use this to plot like to get a report kind of a thing. Okay, and if we will go into the ternary plot, it will give you the ternary diagram. Now usually in the ternary diagram we see that region where there are two phase being separated, but for this three phase mixture, like for this three component mixture, methanol, chloroform and acetone, what has happened is that it doesn't phase separate out into two parts. That's why you are not getting this kind of a LLE plot. If you will remember that there are no tile lines available. So if you will go again to the ternary diagram on the top right corner, yeah, and right now use continue to Aspen plus ternary diagram and just run the analysis. So you will get an error that no plot or table produced due to the calculation error. Press OK. Now can you go to the error part, comments, click on the comment part. Yeah, comment tab. It should show somewhere that no phase has separated. Can you scroll down and see the result at the bottom? Status. Click on the status. It's not showing you. Anyway, for me it was showing that. So basically what is happening, that this ternary mixture is not phase separating out into two parts. That's why you are not getting that tie lines and the phase separated region, like all the points. It's a kind of a singular mixture, and in between you are getting binary and ternary azeotrope. Okay, So this is kind of a just another way of analyzing the whether azeotrophs are formed or not using the Aspen plus distillation synthesis analysis rather than just looking at the ternary plot. Now here you can change the pressure value and accordingly the your ternary diagram will also change. Okay. So this I have included. This is a small basic example. This I have included because it's related to the one question. I think two questions in your assignment. The last question part. Okay. So this was basically related to the property estimation. Now you can stop sharing your screen. Now, okay. Now moving ahead with the two examples which are more interesting and kind of related to the process optimization thing. So this all the regression and the property analysis we did. It was kind of related to finding components property, fitting the best suited method data. Now same sort of regression, optimization or sensitivity analysis can be done in our process model also. Like all the models that we have seen, unit for the unit operation or unit process, the distillation column unit, flash column unit, reactor column unit. There also we can do sensitivity analysis. Sensitivity analysis is nothing but just variation of one parameter with the another dependent parameter. Like we see in the pure component, we see the variation of density with temperature. This is nothing but a kind of a sensitivity analysis, that how density of your pure component varies with the temperature. So same thing can be done in our component analysis. There it's called as sensitivity analysis. So if you will see in the Aspen Plus, if I go to the simulation window, so here I have this model analysis tool where I can see, you see this option, sensitivity, optimization, constraint and data fit. So this is
the screen is not shared.
Oh sorry, oh really sorry. Yeah. So I was saying that in the Aspen Plus simulation part, like simulation window, you can see in the model analysis tool, this one, there are these four options: sensitivity, optimization, constraint and data fit. So this is nothing but kind of a same analysis tool that we have applied on the property analysis of pure component, binary component, but rather instead of applying it on the property itself, now we are applying on the our process part. So whether it could so we will see the few example of it and how we can use this tool to optimize our process plant parameters. Okay, so first question, so it's a big question. First let's read it out what it says, that two streams of water are poured in one tank. Okay, choose the base method as steam NBS. The first stream flow rate is given as 20,000 kg per hour and the other stream is at 15,000 kg per hour, and the outlet stream of the tank. So basically two streams are coming together in one tank, so we have to kind of use a mixture element, like mixture in the Aspen Plus, since we don't have any tank as per se in the Aspen Plus. Okay, then the outlet of stream of that tank is passed through a pump at a discharge pressure of 14 atmosphere with a suction area provided. Pump and driver efficiencies are given. Then this water is transported to the another tank via 1500 meter long pipe. Pipe parameters are given. It's carbon steel pipe with a schedule number and nominal diameter. And the different fittings within this 1500 meter long pipes are provided. We have 2 gate valves, 4 butterfly valves, 12 90 degrees elbow, 20 straight T's. Okay, temperature profile inside the pipe is also given, which is a linear with an outlet temperature of 20 degrees centigrade. The pipe connections are flange welded. Pipe rise is 0.2 meter. Okay, single liquid phase is assumed to prevail inside the pipe. Now it has been asked, choose the maximum number of iteration in the flash option as a 60. That is fine. Change the default conversion method to complex in this step. Write a Fortran code to optimize the diameter, for which given objective function will be minimum by varying the inner diameter of pipe from 250 to 300 meter with a step size of 0.5, and this is the objective function. So if you will see the objective function, right now we don't know what exactly this objective function is, but if you will recall your some of the uh, fluid flow and the designing classes, so we have such kind of equation available where pressure drop of your pipeline or the friction factor of your pipeline are related with the parameters such as diameter of the pipe. Okay, so this is some kind of equation that objective function is given, which we have to minimize by varying the diameter d, which is pipe diameter. Okay, and there are some question asked that we will look into that. So first let's try to model this, and then we will do optimization of this diameter. Okay, let me quickly add the water here. Next method, so we have been asked to use steam NBS. Okay, go next, run the property analysis. Mhm. Mhm. Let it go. Let's see if it takes long. Then if it takes long, then I already have this example with me. We can directly look into that part. Okay, yeah, so it's done. Go to the simulation. So first, it what it has said that two streams are coming and are poured into one tank, and from there outlet stream is pumped at a 14 atmosphere. So essentially there are two streams coming and mixing together. So I will select first a mixer unit. Okay. Sure. We connect to destination. Okay. Then from here the water is pumped destination via pipe. So I will select a pipe unit. Okay, and this connection is not complete. Source. Yeah. Anyway, so now let's fill the details. So stream 1, which is water stream, it's coming at 30 degrees centigrade, 1 atmosphere with 20,000 kilogram per hour flow rate. 30 degrees centigrade, 1 atmosphere, and we have mass flow rate of 20,000 kg. Let me say mass mole fraction of water as 1. Okay. Stream 2 is also water, and stream 2 is coming at 300 Kelvin, 1 atmosphere with a 15,000 kg flow rate. So 300 Kelvin, I'm selecting 1 atmosphere, mass flow rate in kg per hour is given, so that is 15,000, and so it's pure water. Okay, so selected. Now next we have to specify the pump parameters. What happened? Okay, B2. So pump discharge pressure is given. So discharge pressure is 14 atmosphere. Select that. What other information are given for the pump? We know the suction area, which is 600 mm square. So if you will see here, pump suction area we can provide in the SQMM. So this is nothing but the nozzle area. You can see cross sectional area of suction nozzle used in the calculation of NPSH. Okay, so this information is available, so we provide it. We also know the efficiency of pump and driver. So pump efficiency is 0.85, driver is 0.9. So let me select that. 0.85 pump efficiency, 0.9 driver efficiency. Go next. So all the pump data is given. Then we have been provided that this water pump discharge is transported via 1500 meter long pipe. So pipe length is 1500 meter. Pipe schedule is given. So we have carbon steel pipe with, I think, schedule 40. Schedule number 40, and the nominal dia is 6 inch. So 6 inch diameter. What other information we have? So it contains multiple fittings. So if you will see, you have this fitting option here, fitting 1, where you can provide the fitting parameters. Connection type is flange welded. So this is just how pipe, this 1500 meter pipe is connected. I mean, you cannot just produce a single pipe of 1500 meter. It will have multiple bends and joints. So these joints are flange welded rather than the screwed. Okay, so that information is given to us. See, it's mentioned that the pipe connection type are flange welded. Now what other information we have? We have 2 gate valve, 4 butterfly valve, 12 large 90-degree elbow, 4 butterfly valve, and 12 elbows, and 20 straight tees. So this information is there. The temperature profile is linear inside the pipe with the outlet temperature as 20 degrees centigrade. So thermal specification, you can see you can provide various condition of thermal condition for the pipe, either constant temperature adiabatic condition or linear temperature profile, where outlet temperature is given as 20 degrees centigrade. What else do we have? The pipe connection is flanged. Pipe rise is also given. Pipe rise is 0.2 meter. Pipe rise can be provided here, 0.2 meter. The rise in the elevation of input and output part. Okay. Now single liquid phase is assumed to prevail inside the pipe. Choose the maximum number of flash operation as 60. Now here in the flash option, you can see currently the valid phase is selected as vapor phase, but it has said to us that only liquid phase is present. Now if this information is not available to you, you should be able to assess what would be the phase condition. So if I run the simulation with the default value of vapor and liquid only, we will get at some error. We can do that also. We will run the simulation with both liquid only and vapor liquid, and then we will get you will see that we have an error. So the discharge pressure of the pipe pump is around 14 atmosphere, and if you will see both the mixtures, they are at relatively atmospheric condition. So with that and with the pressure value of 14 atmosphere, your pipe will have a single phase of liquid only. There won't be two phase present. So if this information is not given, you should be able to assess it. It's not just like selecting parameters given to you and just putting it out. Obviously this is a systematic question given to you, but apart from that, when you are solving an actual problem, you should put this condition in your mind. And then after it has been asked to do an optimization part that we will see later, but just this all informations are complete, maximum iterations are given, and then we can run the simulation. Okay, so it's running. So what are the questions that has been asked is, what is the NPSH of the pump, what is the equivalent length of the pipe, temperature profile of water at 600 meter length, and then optimum diameter of pipe and the minimum value of objective function. So this question number 1 to 3 are straightforward from their simulation, while 4 and 5 are related to the optimization of the pipe diameter. Okay, so let's see. It's still running. Okay. Results are available. Make sure there are no warnings. No warnings, no errors. Okay. So first question is, what is the NPSH of pump? So block B2 is our pump. Go to the result of that, and you can see the NPSH available. Meter. It's 23.464, and our answer is between 22 to 24, so that is correct. What is equivalent length of the pipe? So block B3 is our pipe. If you will see the result of it, you get an equivalent length which is around 1588 meters. Are we getting that? No. So there is some difference of 1660. So here pipe length is more. Why? There is pipe setup. We have provided all the parameters, right? Schedule number this, pipe rise is also given, thermal specification, fittings 2, 4, 12, 20, and the flash option. Oh, it should come exactly same, or probably it is for the optimized diameter. Let's come back to this part also. Okay. And then what is the temperature of water at a pipe length of 600 meters. So how to check that? So in the result summary of B3 block, you can see the profile option here. This gives you the temperature profile. So with the pipe length at 600 meters, temperature value is 298.39 Kelvin. So that is also coming in the range. The question 2 we will come again, like why there is a difference. Okay. Now what has been asked to us is to optimize the pipe diameter between 250 inner diameter of pipe between 250 mm to 300 mm. Okay. To minimize the objective function, which is this function f. It might be related to the pressure drop or the friction factor. Okay. So in the model analysis tool, you see the optimization option. Click on that. Now we want to add the optimization, so O1 will be added. First you have to define the variable. So there are these four blocks which mainly we will use. One is define. So this is the variable that we will be using to define our objective function or constraint. Okay. Then you have objective function or constraint which we will put here. Vary. So this will be your independent parameter which will be regressed, like on which regression will be done to get desired objective function within a given constraint. And in the Fortran part, you can write a small snippet of your function. Okay. So we want to define which parameter we want to vary. So right now we have been asked to vary the inner diameter, and the function is also optimization function is also in terms of the diameter only. So I can write IND. I am writing it as inner dia. I have to define what is exactly inner dia. So it's a block property, it's a pipe property. So I will select the category block. It's a block variable. Which block? So B3 block, which is our pipe block. And you can search the variable here. So I want to vary the diameter. So diameter, inner diameter of pipe, select it, and we have been asked to regress in the mm unit. Okay, so millimeter. So one parameter is decided. Now this is the parameter for your objective function or your optimization problem. You can have more than one parameter. Right now we have only one function in terms of the diameter only. If you will remember Sir's class, he had used flow 1 and flow 2. Okay, so there were two variables in present. Now we want to minimize objective function f. Right now we have not defined it. We will define what is f by varying again the pipe diameter. So here the independent variable that we will vary is also part of an objective function. It could be that your objective function has a different set of properties which will depend upon your independent variable, but that might not be the part of objective function. Okay. So we want to define again the which is the independent variable, which is diameter of the inner diameter of the pipe. So block variable, I'm searching for diameter, inner diameter, select it, unit, let's keep it in mm. We have been given the bound that change the diameter between 250 to 300 mm. Okay, so 250 to 300 mm. Okay, then now we have defined the variable. We can also define the step size. So step size has been given as 0.5. If not given, then either Aspen Plus will use a default value, or we can you can select on your own also how much accuracy you want in the step size. Okay, now we have to define our objective function. So you have to write the small Fortran code, as in not code, just a snippet. So if you don't know it how to write it, you can use the online tool like search it on Google, or any AI tool should help you to write that small snippet part. So it starts at you have to first leave a space of 8 characters, and then you can start your code. So function is f 1000 times d, f is equal to 1000 times d plus 10 to the power 17 divided by d to the power 5. So 10 to the power is written as e17 divided by d to the power 5. Now here one mistake I have done is I have to, this variable I have to write in terms of this int, like the variable which is I have defined. So you can right click on this panel itself and you can see the variable list. You can just drag and drop, or you can write it directly. So if I want to do this, I can write int. So inner diameter, so instead of d to the power 5 I should write inner diameter to the power 5, and here also inner diameter. Oh, sorry. So we have defined our objective function in terms of the diameter. So all things are set. Now we can proceed for the optimization and see what result we are getting. Okay, so optimization has complete, no warnings are generated. So you can go to the result part and see objective function value is given as 25 into 10 to the power 4. Number of iteration it took was 2, and what is the optimum sampled variable? So it started with the value of 255 and final value came at 250. Okay, you can see the manipulated variable, like the optimum value of our manipulated variable, which is our inner diameter. So bound was given between 0.25 to 0.3 and it converged at the final value of 0.25. With the iteration you can see the objective function value also. So here what has happened, objective function has not varied much, so that's why it has stopped at 0.25, and this is the status. So initial value started with 154.05. Can you guess from where this value came? We haven't provided any initial value, right? So from where this the optimization has taken this initial value? Any idea? So it's related to the input specification of our B3 block. So here we have provided, right, the pipe diameter. So we have provided schedule number and nominal diameter 6 inch. So you will see 6 into 2.54. So that is 15.24 centimeters, right? So that will be 0.152 millimeters, and it has taken 154 around that value. Okay, so that comes from the nominal diameter, like the provided value. But we have said that the lower bound is between 250, and so do optimization between 250 and 300. So it has selected this value. Okay, and this is your summary. So coming to the question itself, what is the optimum pipe diameter? So we are getting it as 0.25. The final value of diameter as 0.25. Okay, 250 so 0.25 meter, and the minimum value of objective function is 25 into 10 to the power 4. Okay, so this is what we are getting. So this is one way of optimizing the parameter based on our user requirements. Okay.
Can I interrupt?
Yes.
Sir, can you take the input? Yeah, same. In this we have objective and constraints, right?
Yes.
Second tab.
Yeah.
In that we are defining only the value f.
Yes.
And that value is defined using the Fortran code.
Yes.
Okay, fine. So only in objective and constraints we just
define
the variable.
So right now we have defined constraint here, like lower bound and upper bound. You can put as a separate constraint also, but generally if it's a bound thing, then you can provide in the variable itself. Let's say there is another objective function, then you can put as a separate constraint. So if you will click here, it will ask you to generate a new constraint, and then you can put it there. Okay, so there are multiple options available. I think here also uh, objective function in terms of the flow sheet variable, right click to select the variable. Yeah, you have to provide it here, but I think in constraint part, let me just show you. So if this is the constraint, so here also you have to add the variable. You can copy paste the variable from there. Let's say if I copy paste this, I have copied it and can just paste it. So it has been pasted. Then you can provide the value of IND, that it should be you have equal to, less than, greater than 250 mm, right? With some accuracy, like say to the power -3. You can give this error. If you have some equation in your constraint, you can write in terms of the Fortran part also, and this we can include in our input. Okay, in the objective and constraint, you can include it. Okay. So there are multiple ways of. It will depend upon your problem how you want to include different constraint. Okay. Now coming to the question number 2, that what is the equivalent length? It had came initially saying for me block 3 results. Okay, so I think after optimization it came down to this value 1649. Okay, let me remove this first, delete. Run it, results are okay. Now stream summary. Results. Yeah, equivalent length has changed. Mixture, heat duty profile, balance. Temperature profile, it has almost remained same, like 600 Kelvin, 298.39. So temperature has not varied much. Okay, so this value equivalent length was with respect to the newer optimized diameter rather than the previous value. Okay, so this is one way of optimizing. Like right now we have selected very basic example. So this again, this F is not defined here what exactly it is, but it could be you have various pressure drop equations in terms of pipe diameter or in terms of various fittings that you have. Okay, so you can utilize that and find an optimum diameter or optimum length for which you get a minimum pressure drop, so that your pumping cost will go down. Since it's a 1500 meter pipe, it's very long pipe. Okay, if you will think about it. So in that case you might need some optimization so that minimum power consumption happens to transport your fluid from one end to other end. Okay, similarly for your cases, like you adapt and modified various parameters. Now the second example of optimization, so here we will do sensitivity analysis, like all these tools we will use. So we right now we had used optimization. So you can use sensitivity analysis also, data fitting also. So data fitting is when you have some experimental data available for any of this operation or process, then same way we were fitting the NIST data to meet and to optimize the model parameter, we can fit an experimental data to optimize an process parameter. It could be, let's say you have reactor data for CSTR or PFR experiment, and then you can modify it or optimize the given reactor parameters based on that. So data fitting example we are not going to do, but this too we will try. Okay, so it's already 8 o'clock. So what I will do, I will just call out a new simulation. I have already Run one simulation, optimization reactor. Yeah, this one. Okay. While it's loading, let's go to the question. So we have been given the optimization problem of reforming reaction. So this reaction part is taken from, I think, your previous assignment, three or four probably. Okay. So you have been given the reforming reaction where methane is converted to hydrogen and carbon monoxide, where again secondary reaction of carbon monoxide with water takes place and hydrogen and CO2 are formed. Okay. First reaction is reforming, second reaction is water gas shift reaction. Okay. We have to use model reactor or equilibrium reactor. Consider natural gas as a poor methane being fed to the reactor at 450 degrees centigrade and 34 bar. Steam conditions are given. Steam condition is at 300 degrees centigrade, 34 bar. Molar flow rate of both methane and steam is given. And then reactor operating conditions are 500 degrees centigrade, 34 bar. Peng-Robinson equation of state we have to use. And answer the following, not 3 questions. Sorry. What happened? It's not editing. Yeah. I think this is also stuck some. So first is like analyze the output flow. You can see my screen, right? There is no interruption there. Okay, I think you are here. So we have to analyze the output flow of product with the variation in the temperature of reaction. So basically we will change the reactor temperature and see the how product varies. Then we have been asked what is the temperature of the reactor required to reach a specific output flow rate, and then one objective function is given in terms of the profit. If profit is given as a function of mass flow rate, where function f is given in terms of the mass flow rate of all, then optimize the reactor temperature to maximize this profit. Okay, so let me close and restart it. So first part should be relatively easy, like it's a kind of your previous assignment question. So you just have to add your component and see what is the outlet vapor composition at 500 degrees centigrade, and then after we have to do the sensitivity analysis. Let it load first and then I will directly show you. Too long. Recording is still going. Here I forgot to run that analysis with vapor and liquid. So as I was saying that uh, here it has been provided that only one phase is prevailing inside the pipe condition, while default it had selected vapor and liquid. So if you will run with the vapor and liquid both, then you will get an error that okay, you will get a warning. So be mindful of such options that you are selecting. I think we also forgot to change the conversion method. Anyway, it should not make a difference. So here the conversion method, we instead of SQP, we have to change it to the complex method, so that you can select from this going to the conversion option on the left hand side panel of the Aspen Plus, then option and default and default methods. It's a small part, it's not a big deal. Again, it's not running. Can I get your any mail address of any of you so I can just mail it to you? I just want to finish this so that from next lecture onwards we can work on various case studies. Nigil or Tanmay? Sorry? I cannot hear you properly. As in, you have access to Aspen Plus. Can you share your screen if it's possible? Then I can share this file and just show you quickly.
Not have a proper mic, so if I have to flip there, then it becomes a problem. So I
Oh, okay,
have
okay.
to.
Okay, no issue. Then Nigil, can you... Nigil, are you still here or not? Okay.
Yes, sir, yes.
Just give me a minute. Let's see. Documents. Okay. I have mailed it to you. Can you check and download it? Let's see. Mhm. Yeah, it has opened up in my screen. Okay. Why this is... It's okay, Nigel. It has opened up, so I will share my screen again.
Okay, sir, okay.
Yeah. Okay. So let me quickly go through the components. So components are this reaction, all the components: methane, hydrogen, CO, CO2, water, and the method is Peng-Robinson. So I have selected the Peng-Robinson method. Run the property analysis, then come to the simulation part. In the simulation, okay, I will show you why this deactivation sign comes. So what we have done here is, in this stream, S1 and S2 are your input stream. So S1 is methane, which is coming at 100 moles per hour at this condition. S2 is, sorry, not S2, S4. S4 is your water, like water stream, which is coming at same 300 degrees centigrade, 34 bar at 250 kilomole per hour flow rate. And in the block, we have reactor block, which is our equilibrium we had selected. Temperature conditions are 500 degrees centigrade, pressure is 34 bar. Varied phases are vapor and liquid we have given, and the reactions are added. So this is the same part that you might have done in the previous assignment, okay? And you don't have to do anything, you have to just run the, so let me first deactivate all the optimization stuff. So this is just a basic flow sheet with a problem here. So it's just an R equilibrium problem. I'm running it and I got the result. So if you want to see, you can see the stream results, that this is the outlet composition at 1500 degrees centigrade. So if reaction is taking place at 1500 degrees, sorry, not 1500, sorry, 500 degrees centigrade, then the CO2 in the outlet composition will be 427 kg per hour. This is the CO composition, this is the hydrogen conversion. Okay. Now what question has been asked, that we have to analyze the outlet flow of a product with the variation in the temperature of reaction. Okay. So for that, go to the model analysis tool and we will go to the sensitivity part. Here, let me make it active. So in this sensitivity part, I have created one variable. So that is a block variable. Block variable 1 is created, which is temperature of the reactor. So you can see block 1, its temperature in degree centigrade. The limit I have provided, so I have taken a long limit from 300 degrees centigrade all the way to 1500 degrees centigrade with an increment of 25 degrees centigrade. In the define, so it hasn't been asked like what exactly to see, but our products are hydrogen, CO, CO2, and there will be some unconverted methane and water. But right now I'm not concerned with the water, so I have not selected it, but I am looking at the flow rate of all four, hydrogen, CO, CO2 and methane, since these are the main component for us right now. So all four variables are added. So if you will look at the VCO2, that is nothing but a stream variable. S2 is the vapor phase that is coming out from the reactor. Okay, this S2, and that is a mixed stream, of which I am interested in the flow rate of the CO2 in kg per hour. Same way you add hydrogen, methane and CO flow. Okay. In the tabulate part, you can select which variable you want to. So all these variable we have defined. This is the input independent variable which will be varied, and these are the dependent variables. So which dependent variable you want to see. You can select one also, or you can just click fill variables and it will add all the variables present. And when you will do the run, results are available. So you can see your results here. Let me plot it out. So with the temperature, we have these all the flow rates present. Okay. Our x-axis will be reactor temperature, and y-axis I want to see all the flow rates, so I'm selecting all. Let me make one y-axis, single y-axis, and do OK. So this is how the profile will look like. Okay, so you have methane. Initially at 300 degrees centigrade, methane is coming like it's 1600 is around the value flow rate of the methane that has been given to us. It's kg per hour. So if you will see block 1 stream summary, the flow rate of methane is somewhere around 1600 kg per hour. Okay, so oh, plot went away, sorry. To do it again. With the temperature, methane conversion happens and it goes down. But then for the hydrogen and CO part, we have intermediate reaction happening. So initially CO2 is more, but then it's again going down. Carbon monoxide initially is less, but then with the temperature its values is increasing. And for hydrogen we get a steady state kind of a region after some 1200 degrees centigrade. Okay, so this is how the product profile looks like. So this is the sensitivity analysis that we have done. Now what has been asked to us, like here you can see with temperature there is much variation. So if you want to get a specific composition out of the reactor, you have to find out what temperature you want to work with. So let's say the question number 2 asks what is the temperature of the reactor required to reach the outlet product flow as. So methane and hydrogen flow rate is given. If methane is 508 kg per hour and hydrogen is 465 kg per hour. So if you will see from this plot analysis itself, if I look at the tracker, so this is for CO2. I want it for hydrogen, so green plot. Yeah. So for hydrogen flow rate, it's asked as around 850. We have been asked like hydrogen flow rate 465. So when we get the 465 value, somewhere around here, around 850 or 850 degrees centigrade. Okay, and similar to at that point, methane is so 850 methane value is somewhere around 506, 508. Okay, so this is from the graph, but let's say you want to pinpoint that value through the analysis itself. So right now what I will do, let me deactivate the analysis sensitivity part, and in the model analysis, not the model analysis tool, here you have this design specification like flow sheeting option, and this design specification. In the design specification, if you will create a new input, I am defining the flow rate of both methane. So VCH4 is selected as a flow rate of methane in kg per hour in the S2 stream outlet of the reactor. Same I have selected the hydrogen flow rate. So two variables are defined, and then you can select the specification of your variable. So right now I have selected that VCH4 should be 508 kg per hour with the tolerance of 10 to the power minus 3. And variable, what will be our variable? That is nothing but the reactor temperature. Now here I have narrowed down this temperature search from 800 to 900 degrees centigrade. since we already know from that plot, this will be 850 is 8 degree centigrade is the range where we get the same value. Okay, so if you will run it, this will be your result, that at around 850 degree centigrade, both VCH4 and V hydrogen will be 508 and 465, which is around desired value. So our answer will be 850 degree centigrade. So by this you can decide at for a desired output what condition we should operate. Okay, what condition are either process unit operation or unit process should operate. Then last question is like, if profit is given in the it's a function of the flow rate, mass flow rate. So this is function f. It's a random function that I have created. Okay, it's not a exact thing, but let's say hydrogen is a desired product, since it's a valuable energy source. Methane will also have some value, and then CO2 we can utilize in some other process, while carbon monoxide we don't want. So that's why it's associated as negative, and this is how some profit function has been defined. So we have to optimize reactor temperature so that this function, like, we get a maximum profit. Okay, so for that, like in the previous example, create one optimization part here again. So there are 4 variables in our function. Okay, flow rate of hydrogen, methane, CO2 and CO. So define all the 4 flow or all 4 variables. Then objective function f, which is profit, we have to maximize. So I have selected maximize by varying again reactor temperature, and bound I have kept from 300 degree centigrade to 1500 degree centigrade. And equation you can add the Fortran equation. So this is our objective function, and when you will run this analysis, results are available. What happened? Let me status. Let me just reset. This will take some time. So like the previous case where we had to minimize this function f, right now we have to maximize it. So it will find all the suitable conditions. So we saw that plot that methane is decreasing, hydrogen is increasing and then is getting steady at one plateau region. CO2 is increasing and then decreasing again, while CO is initially low but then is increasing higher. So in somewhere in between we will have a region where the profit will be maximum based on the all the conditions of all the flow rates that are available. So our optimization output should give us that specific condition. And you can see that temperature will be somewhere around 644 degrees centigrade, where you will get this maximum profit part. Okay, so results are available. Why it's not showing end result? This is deactivated. Sensitive. Oh, yeah, it's here. So you can see uh, objective function value is given as a 4022. It has done number of iteration on the last loop 4, number of flow sheet passes on the last outer loop 18, and these are the values for which you will get a maximum profit. So methane flow rate should be, this is the final value, so somewhere around 1200 kg per hour. Hydrogen should be 195 kg per hour, and CO2 and CO respectively. So what is the corresponding temperature manipulated variable? This is coming as 641 degree centigrade, and this answer is 645. So since it's an optimization problem, it might converge differently depending upon your iteration. Okay, and you can see with the number of iteration how the value of objective function change. So initially it started with 500 degree centigrade. This was the objective function. Then after some iteration, you can see almost the value is constant, so it had decided to converge it. Okay, so this is how this model parameters can be used to optimize your process aspects. Okay, so this was it for today's class. I hope you understand all the points. So I will stop the recording now and we can end it here.